This webinar is brought to you by Ghana Medical Help with collaboration from the Ghana Health Services and the Canadian Medical and Biological Engineering Society. My name is Dominic Akaateba. I'm a medical doctor at the Kolebu Teaching Hospital. I work also as the country director of operations for Ghana Medical Help. This, in our series of webinar, for those of us who have been joining the previous ones, is aimed at improving health service delivery by way of clinical engineering, education, as well as improving their skills. We've, despite the COVID pandemic, have been able to, with gracious contributions and time dedication from Bill and Martin, as well as Mr. Zienaa, organize this series of webinars to help us in going about our education, as well as our practical bit, which was originally scheduled to be an in-person session, but for the COVID. We are happy today to have Bill and Martin leading us for this webinar, essentially on troubleshooting, as you could see from the flyer that we put up, the principles of effective troubleshooting. It's going to be a participatory one because most of what has been put up was learned from our own feelings and our own inputs as Ghanaians and in the developing world, how innovative we've been. So without much ado, I would hand over to Bill and Martin to take us through this session. You are very much welcome, and thank you for joining us.
Thank you, Dominic, and welcome everybody. I'm glad you are able to take the time to join us today. This is the fourth in our series of webinars, and I'll now hand the screen and the microphone over to my co-host Martin to give the first few slides. Over to you, Martin.
Thank you. So good afternoon, everyone. It's an early morning here. I'm on the west coast of Canada, so quite a distance away. But we're here today to go over our perspective on the principles of effective troubleshooting of medical devices. And we're going to start just giving some thoughts on some general troubleshooting principles. And then we've established 15 rules of troubleshooting that we'll go over in more detail. And then we're going to go over some of the innovative repair examples that many of you have provided in Ghana. And then after that, we'll have a few questions where we're going to try to solicit some feedback from you via the chat window. So just initially starting with some thoughts on some general troubleshooting principles. The first thing to acknowledge is that medical devices typically do not have high failure rates, and the majority of all problems are related to improper use or maintenance. Examples of improper use are things like improper cleaning or no cleaning, sometimes causing poor airflow and therefore overheating, poor preventive maintenance, and sometimes operators that don't understand how to use the device properly. Next slide. So there are three things that we would want you to think about. One, start by looking for the obvious things, obvious problems. Two, just think about it in simple terms. And three, don't overcomplicate the problem, because often if you just look at the device and understand how it functions, you can often determine where the fault is. Now, most troubleshooting steps don't require a service manual or expensive test equipment. Of course, it's desirable to have those at your fingertips. But if you use your eyes, ears, and nose, and your understanding of how the equipment is used and how it functions, that's your best approach. So some of the rules that we've established. The first one is to collect information. Always confirm the problem yourself. Don't rely on the diagnosis of the clinician because they might not have it correctly. and talk to the person and the clinician who reported the problem and to try to get some understanding how the machine operates and what are the symptoms of the problem to help you move forward with diagnosis. Check the equipment records, if there are any, for the repair history, because this may give you some insight into similar problems that have occurred before. And ask your fellow technicians, they may have also seen similar problems. And finally, check if the equipment is under warranty, because perhaps you can turn to the vendor for assistance. So rule number 2, start with assessing the external factors to the equipment. So is it plugged in? This covers not only the power cord, but also the signal and power cords in the system of interest. Check and firmly seat all plugs. Is it actually turned on? Medical equipment sometimes has more than one power switch. Is the plug good and installed completely? Lack of proper installation of plugs has been disproportionately responsible for power losses and intermittent operation in portable equipment. Is the wall socket live and solid? Loosely mounted, damaged, smoke stained, heat damaged wall outlets are likely to be dead or intermittent, and that would need to be resolved first. Is the wire next to the plug good? Any plug that is handled often will have fatigue failure, typically just adjacent to the plug, as indicated in the image here. And to make sure that it's that where you may have a wire break at that location. Rule number 3, investigate for possible operator errors. Ask the operator what controls they used immediately before they encountered the failure. So check the position of all switches and controls to be sure that they are correctly positioned and working. Check for the intended use to make sure that the equipment is being used appropriately. Check that the correct supplies are being used. And does the operator actually understand all the functions of all the controls, because they may have switched something inadvertently. Assuming there are no signs of mechanical damage to the device, do a self-test or calibration of the device. This may also give you the error log on the device, which you can review and help with the diagnosis. Unfortunately, all too many techs will stop the process if the self-test passes, but there can be other problems that are not part of the self-test process. So you want to make sure you do a complete, full troubleshooting before returning the device to use. Rule number 4, check for cable problems. Connectors, power cords, and input or output cables. Are they in the correct position? And are they secure? Have they been damaged in some fashion? Maybe there are some breaks. You want to take a good look at the full length of the cables. Check the inputs. So where does the actual input come from? Well, of course, the patient. So has the patient's condition changed? Has the patient's temperature gone up or down? Is there more movement, like shaking or shivering or thrashing? Did an electrode or sensor fall off, or its contact resistance go up? Are the lead wires and cables good, like rule 4? Did you do a self-test or calibration on the device? Perhaps there's an error message. And then go back to rule number 3 and listen to the user. Sometimes they have the answer, but are not sure of it, so they call you to confirm what they thought. If or tissue samples are utilized, are they properly prepared? Are the samples being presented correctly? So just some of the things to think about with respect to checking the inputs. So are there problems with the output? Delivered energy can be light from a laser, ultrasonic energy from an ultrasound device, or high frequency energy from like an electrosurgical unit. Fetal ultrasounds have 2 outputs, one to gather the data and the other to convert the data into an audio tone. Diagnostic ultrasound also has several outputs. From the transducers, energy is delivered to the target, and the balance of that energy is processed into visual outputs on a monitor. The most common devices with output graph recorders, such as electrocardiograms or electroencephalography. The problems with those graphs, so they often have the paper is not installed correctly, or the paper is not moving at a constant speed. Other problems involve dirt or wax buildup on the print head or stylus. The alphanumeric output from some devices is displayed on a monitor typically, or it's printed on a sheet of paper, or placed on a continuous roll of paper like the ECG, or sent by a network to another device. When the output of one device serves as the input of another device, there can be problems with the transmission of the data. Be sure to isolate the problem as either an output, an input, or a communication problem. Some devices will require specific test equipment to determine the output level of the device. Rule number 7, should check the error log if it's available. So some equipment these days, they have event recorders and or error, they identify an error code. So they have a little bit of intelligence in them that you can take a look at if you're a service technician. And these error logs can often help you to diagnose the problem. This is an example here from an infusion pump that lists some of the status of the device. And you can see at the bottom, it's indicating battery low. So give you some insight into how to resolve this problem. Check performance, then check the output performance specifications to make sure they're within tolerances. So you want to check that the output device meets what's set on the dial. So some examples could be the oxygen percent of an oxygen concentrator to make sure that it's meeting what the device is set at. Another example could be an electrosurgical unit, and you want to check the actual power output is matching, again, what the output of the dial is set at. Those are the kind of things that you need to take into consideration. So I'll just move on to let Bill move on for the next rules.
Thank you, Martin. Now, I'll pick it up at Rule 9. Okay, you've done all your diagnosis on the outsides of the machine. It's time to take off the cover and look inside. Again, many of these troubleshooting rules require no knowledge of the schematic diagram, no knowledge of a technical manual, just using your eyes, ears, nose, and your intelligence. Are there signs of heat, smoke, burned components, unusual sounds? Often you can see or smell overheated components that will lead you to problems inside the device. A typical failure point is the fuse. Are there blown fuses? You can often, but not always, see a blown fuse because sometimes it's a very tiny filament that's hard to see, so you may need to check it with your multimeter. Is there an internal battery? Is it good? How old is the battery? Perhaps it's just a small coin cell that's used to store memory values that may have died if the device is very old. Are there any dead fans that you can see that are supposed to be spinning and they're not? That could cause overheating of other components. Okay, Rule 10, look for dirt, dust, and spills. This is a not too unusual shot of the inside of a machine with cooling fans that have never been cleaned, which can sometimes cause the fan to stall and lead to heat buildup. Look for dust or spills on circuit boards and signs of heat buildup. Rule 11, try and isolate the problem module. There may be a number of circuit boards plugged into sockets. Are they properly seated? Can you check the proper operation of each module? Sometimes there are little indicator LEDs on the module indicating presence of power or functionality of the module. Check the interconnections of the cables between modules. Are there loose connectors? Connectors not in place? Signs of heat or damaged components? Are there components coming loose on the boards? Now at this point, it would help if you have a technical manual that explains the function of each module and how the signals flow from one module to another. But in any case, you can still do a lot of troubleshooting without the technical manual. On the next slide, just some pictures of visual clues of problem components. And the first place to look for failed components is the power supply. The power supply in an electronic device is usually the most common point of failure. Components in the power supply that are vulnerable to failure. The most common is the electrolytic capacitor that's used to smooth out the rectified voltage. Capacitors can reveal their failure by distortions of their size, bulging, or leaving residue on the circuit board, as shown in the right-hand picture here, that are indications that the capacitor is leaking some of its electrolyte. And these are very common problems with power supply boards. And we'll get into some real-life examples that some of our Ghanaian colleagues have submitted at the end of this the formal presentation. Rule 12, again, looking for problem components, and bad diodes is another common issue in a power supply. Typically, if the electrolytic capacitors have failed, they may have gone to short circuit, and as a result, consequent blown some of the rectifier diodes. So a failed capacitor may lead to the failure of other components, such as diodes. In addition, cause overheating of resistors by a shorted electrolytic capacitor. And this can often be seen by just looking at the resistors for carbon deposits or signs of overheating. And Rule 13, moving on to Rule 13, use your networks to share problems and solutions. Now, you've got a very effective WhatsApp network in Ghana, and I just encourage you to use that to share some of your problems, technical problems, as well as your successes. I'll just give you an example of a success we had in Canada when I was running a biomed department. We had a fleet of bedside monitors that were about 5 years old, and they started to fail. We isolated the problem to the power supply module. The power supply module had several output voltages. They were all 0 volts. We could measure them, but the vendor refused to supply us with a schematic diagram for the power supply module. They instead offered to sell us replacement modules for $1,000 Canadian, which is about 5,000 Ghana cedis. We put out a message on a Canadian email list server at the time, which was shared across the country, asking if anyone else had had this problem. Somebody a couple of thousand kilometers away in central Canada had the same brand, make, and model of patient monitor that he'd had in service for about 6 years. So his power supply modules had started failing about a year before us. And he had isolated the cause of the failure to a single electrolytic capacitor in the power supply. It was a switching power supply, which those are notably very tricky to troubleshoot, especially when all the output voltages have gone to 0. He had managed to find one electrolytic capacitor that was repeatedly failing. Available at a local electronic supply shop for about $2 or 10 Ghana cedis. Replaced that capacitor on probably 4 or 5 of these power supplies and saved our hospital thousands and thousands of dollars, simply by connecting with a colleague in another part of the country with our problem, and he provided us with a solution. So I strongly encourage you to use your available networks to share your problems with others, because many heads are better than one in solving these problems. So last couple of rules here. Rule 14, after you've done any repair, you should always perform a preventive maintenance procedure and a calibration check before returning to the user. Return all the controls to their original positions and make sure that the device is functioning according to its specifications so that you don't get a repeat service call simply because some setting is in the wrong position. And rule 15, please keep a record of all work done. Document your work in the database if you have one. We're hoping soon to be able to provide everyone across Canada with a functioning maintenance management database, but even keep a paper record of the work you've done or put it on a spreadsheet. This helps in troubleshooting future problems with the same device. Now, just to move to some examples we've received from our colleagues in Ghana that illustrate some of these troubleshooting concepts. And the first one, this is one of my favorites. When repair parts are unavailable, you can often improvise and replace things with something equivalent. In this example, thanks to Clement for this example, the centrifuge motor carbon brushes are worn out. Now, carbon brushes are illustrated on the right in this picture. It's a block of carbon on a spring with a copper wire connecting it to the source of power, and it delivers current to the rotor of the device. The carbon brush is made of a soft material that is meant to worn out. It contacts conductors on the rotor of the motor, which are typically made of copper, and you don't want the copper elements to wear out, you want the brushes to wear out, but they typically wear out after a few years of use. And often if the device is old, the vendor is no longer supplying carbon brushes. So Clement found a very innovative solution to replacing these brushes. As you all probably know, carbon zinc batteries contain a cylindrical carbon rod in the center of it. Clement managed to extract a number of these carbon rods and grind them into a square shape just by rubbing them on a flat concrete surface. Rubbed them to approximate shape of the old carbon brushes, verified the fit, inserted them with the original spring into the motor, and got the motor successfully up and running. This put the centrifuge back in service. But we have a rather nice video of this motor running. Because of bandwidth, we're not going to show the video today. So that's a lovely example of improvising where the replacement parts are unavailable. Another example in that theme is was provided by John Zienaa. Thank you, John, for this example. An autoclave had 4 solenoid valves that had failed. When they removed the solenoid valves, they found that the fittings were not compatible with any locally available valves. There was a locally available valve with similar specifications, but it had different fittings to fit to the plumbing. So John and his colleagues managed to make new fittings by machining them locally to adapt the new valves to the existing piping. And as a result, managed to put the autoclave back in service, and it's been running satisfactorily ever since. Another example now. And we've talked a lot about power supply failures. This is a common problem. And in this example submitted by John Iden. A spot vital signs monitor has repeated power supply failures. The existing power supply was vulnerable to the power fluctuations which are common in Ghana. So the solution to this problem that John came up with was to design a power supply with the same specifications that was less sensitive to the power fluctuations in the local power system. This same power supply can also be used to charge the battery in a patient scale. It's a simple linear power supply with a transformer and a regulator. Another example of a power supply problem. Thanks to Kobina Deborah for this example, there was a blown power supply board on a C80 anesthesia monitor. This power supply board could not be repaired and a replacement for it was unavailable. Very similar to the example I gave from Canada. In this case, the monitor is rated at 60 to 68 watts. It has an isolated voltage regulator which distributes voltages to all the other boards on the monitor. Shown in this picture, the red arrow points to the existing power supply. In the next picture, we see a power supply from an old laptop was found that had similar specifications and was inserted in place of the defective power supply inside the monitor. It's now been in use for 2 years with no problems. Another beautiful example of substituting parts when the OEM parts are no longer available. A third example of a concept when you have a poor design that is prone to failure in the local environment. Thanks to Kobina Deborah for this example. A burned out heater on a distilling plant was frequently happening because of water shortages. The heater burns out when there's not enough water in the distiller. Thus, the user is required to monitor the distiller frequently and turn the distiller off when the water level goes low or the water supply is cut off. When you make demands on the users that require repeated attention to a rather uninteresting task, it's asking for the users to not pay attention at the critical time and cause failure of the device. So this was a poor design. It needed to be fixed, otherwise they were going to repeatedly have failures of the heating element. Solution was to design a water level controller using a level switch, a contactor, and other components. Now when the water goes below the minimum level, you can see in this picture the water level sensor was installed inside into the side of the distiller, and the other components are mounted on the wall. When the water level goes below the minimum level, power to the heater is cut off. Then when enough water is detected, the heater receives power and comes on. This intervention has safeguarded the distiller for 2 years now, and it is still running satisfactorily. So I'll just summarize, and then we're going to open it up for discussion and send you some questions. Just in summary, start by looking for the obvious, think simple. Most troubleshooting steps don't require a service manual or expensive test equipment. Use your eyes, ears, and nose. Follow the 15 steps. And with that summary, we'll now hand it over to Martin. We're going to throw out some questions for participants just to get some discussion going. Please answer these questions in the chat window. Over to you, Martin.
Yeah, so it's difficult certainly on this platform, but we're going to try to get some feedback from you, the participants, by getting you to type your answers to the following questions. We have 5 questions. So when you answer the question in the chat window, perhaps you can make reference to say, this is question 1, and here's my answer. And then I will try to do my best to collate the answers and give you responses or give the responses back to the entire group. So I'm just going to read all 5 questions, and then we'll go, Bill, I was just going to go through them, and then we'll go back to question 1 so people can start thinking about them. So the first question is, what is the most common cause of equipment problem that you've been seeing? Is it A, electrical power fluctuations, B, component failure, or C, user error or misuse? So think about that, and if you can try to note in the chat window your answer to question 1 is either A, B, or C, that would be great. And then so there's just the next question then, number 2. What is the most common component failure that you have found? So if you can indicate question 2 and what is the most common component that you think you found that has failed? Question 3, can you give us some examples of any glaring operator errors that we can share with the group? Question 4, how often do you communicate with your colleagues about technical problems? And then question 5, can you share with us any other troubleshooting examples? So let's just go back to question 1, and I'll if you can each type into the chat window so that we can see what your answers are, then perhaps we can try to collate.
Now we're very interested to see how you perceive this issue in Ghana, because we have opinions about it in Canada. I know my experience is that at least 2/3 of the problems are error or misuse. User error is the most common cause of a service call to a biomed shop. Now, but in Ghana, it may often be electrical fluctuations, as we've seen here in a couple of responses. Let's moving on to question 2. Some of these are answering question 2 now. Capacitors, transformers, MOVs from power surges, I guess. Varistors, metal oxide varistors that are used to protect from power surges. Fuses. Question 2, component failure, MOVs. This is interesting.
Mm-hmm.
We would almost never see an MOV failure in Canada. This is great. Thank you all for submitting these, and keep them coming. Now let's move on to question 3. Question 3. Can you give examples of glaring operator errors? I'll give one just because this always comes to mind. When my first child was being born, we were in the labor room and the nurse wheeled in a fetal monitor and she put it across my wife's belly to monitor the baby as my wife was in labor. And then she looked at the monitor and said, "Oh, it's not working. I'll go get another one." And I said, "Wait a minute, I'm a biomedical engineer. Let me take a look." I looked around the back of the machine, and the power cord had fallen out of the back of the machine. I plugged it in, and the machine was working.
That's interesting, Bill. I had a similar incident when my first daughter was being born. And they couldn't figure out how to turn it on, and it was simply a power switch was hidden.
At the back of the machine. Oh yes, and here John Iden has experienced the same issue: power cable disconnection.
Right.
Mismatch of EC probes during connections. Poor disconnection of probes. Connecting a 120-volt device to 220-volt wall socket. That's a common problem with donated devices, which are donated with the wrong voltage. Cuff not fixed well. Cuff not attached to the patient well. Failure to connect the power cable correctly and switch it.
Bad batteries.
Batteries. The device will usually tell you when its batteries are not working.
Another example here.
Question 3, yeah.
Cleaning of humidifiers on oxygen concentrators. Supposed to be regularly cleaned, but nurses always forget to clean. The residue blocks the pathway. They call me telling me the concentrator is not working, but it's actually just, it's blocked.
Needs to be cleaned. Okay, let's move on to the next question. How often do you communicate with your colleagues about technical problems? This is a more philosophical question, I guess, than a technical one.
Very often is the first response.
Always.
Some more responses, always, very often. Very often, especially with devices I've little knowledge of. One comment, not always communicating, another most often, often. And I'm curious if you are communicating just with colleagues that are close to where you work, or whether you communicate with colleagues across the country. I'm sure if someone can answer that.
And there are, I believe there are some efforts to develop a kind of connection of biomedical societies throughout Africa, which I'm not sure if you're aware of that initiative. I think it's maybe coming out of Nigeria or South Africa. So I notice here from Clement, there is a biomedical engineering platform in Ghana. Are you aware of other international platforms? So Infratech, I'm glad someone mentioned Infratech. This is a global email list server that is subscribed to by, I don't know, about 80 countries around the world. You can post a question if you're looking for a technical manual, or you're having a problem with a device and you can't solve it locally. I encourage you to send me an email and sign up for the Infratech email listserv, and you can post questions and get answers from people around the globe. Okay, the last question. Looking for troubleshooting examples that we haven't already shared from Ghana that you think might be interesting for others to hear about. Here's an interesting one from John Idan. Software settings, changing degrees Celsius to Fahrenheit. Often that's a tricky thing in some service menu that is buried inside the menus of the machine and may need some service password to get at it.
This has all been very good feedback, though. Thank you everyone for putting your thoughts down.
And I think we're getting close to the end of our time. Just wait a few more minutes if people have other comments or questions of a general nature that you want to raise at this point. We're opening the floor for anyone to make a point or ask a question. In the meantime, I'll move to the last slide and provide you with the link we ask at the end of every webinar to please fill out the survey. This is the way we award the certificates. If you've attended all of the webinars, you get a certificate of participation from Ghana Medical Help. And the post-webinar survey for this webinar is this link, and I point out it's a bit.ly link, bit.ly/3 lowercase l, lowercase I, lowercase w, uppercase L, uppercase Y, lowercase g. So copy that link. Please fill out the survey afterwards. If you watch the webinar on YouTube and fill out the survey, you're also eligible to receive the certificate. So we encourage you to pass the word on to your colleagues if they have not been able to join us today because of other commitments. And I'll then maybe pass the microphone over to Dominic. If you could just make some closing remarks, Dominic.
Thank you very much, Bill, and thanks to Martin and Mr. Zienaa, and thanks to all the trainers and those who put up all this with the experience and the pictures shown from our planning team, John Aidan, Sebastian, Clement, and everyone who put an effort into making this webinar a success. We so much grateful. Like Bill said, please make time to fill in the post webinar survey. It helps us to be able to serve you better. As well, it helps us to be able to get your name and your details to fill in the certificate as appropriate. Till we meet next time. Over to you, Bill, if you have something to say. Thanks.
Thank you, Dominic. And just a reminder, please fill out the survey, and we will be announcing another webinar in about a month's time. And we hope you will join us for our next webinar. Thanks for all of your questions and participation. Bye for now. We'll keep in touch.